Look down, right now, beneath your feet, in the cracks of the sidewalk, under the bark of a tree, or deep within the foundations of a skyscraper, lies the true global superpower. They are everywhere, they are relentless, and they outnumber us, not by millions or billions, but by the staggering, incomprehensible figure of nearly 10 quadrillion individuals. They are the ants. For centuries, we've dismissed them as simple pests or tiny, solitary nuisances. We see the lines crossing our path and think, an inconvenience. But this surface-level interaction blinds us to the monumental reality. These creatures are not individuals. They are components of a colossal, interconnected network. They are the living, breathing infrastructure of every terrestrial ecosystem on Earth, thriving in environments from the scorching deserts to the damp, mossy tundras. If you weighed every ant on the planet, their collective mass would exceed that of all wild birds and mammals combined. This isn't just about weight, it's about kinetic energy, the cumulative force of all those moving bodies constantly tilling soil and harvesting resources. They are the hidden weight, the invisible hand that tills our soil, disperses our seeds, and shapes the landscape more profoundly than any animal in history. They have mastered agriculture, perfected chemical communication, and evolved a social structure so advanced it makes human civilization, with all its internal conflicts and resource inefficiency, look like a chaotic, fleeting experiment. Their sheer adaptability and specialization have allowed them to colonize virtually every corner of the globe. They were here before us, and they will likely be here long after. To understand the empire, we must first understand the individual unit. The ant is an insect, of course, but one highly specialized for communal living. Its body is a marvel of efficiency, clearly divided into three distinct segments: the head, the mesosoma or thorax, and the gaster or abdomen, all connected by one or two slender, flexible waist segments called the petiole and postpetiole. This narrow, highly articulated waist allows the gaster incredible mobility, crucial for defense, stinging, and chemical marking. It acts as a pivot, allowing the ant to defend its colony or spread pheromones with precision. The head is a command center dominated by powerful mandibles. These aren't just jaws for eating, they are multi-purpose tools. Depending on the caste, they can be weapons of war, powerful scissors for cutting leaves into fragments, or tiny, delicate forceps used for tending to the most vulnerable members, the larvae. The musculature within the head, required to power these jaws, is disproportionately massive compared to the ant's size, granting it its legendary strength. And their sense of smell, exponentially superior to ours. Located on their pair of jointed elbowed organs known as antennae, their olfactory senses detect and decode the subtle chemical language of the colony. The pheromones. The antennae are constantly in motion, tapping, vibrating, and analyzing the environment. They act as both their nose and their primary means of tactile communication, touching other ants to exchange essential information about food, danger, or identity. This chemical language is the very fabric of their society, creating a world governed by scent. Ant life begins not with a birth, but with a complex four-stage metamorphosis: egg, larva, pupa, and adult. The egg is microscopic, usually oval, and often sticky, to allow workers to carry masses of them easily from chamber to chamber, constantly seeking the ideal humidity. The larva stage is the most vulnerable and energy-intensive. It is essentially a C-shaped, legless feeding machine, and it is entirely dependent. It cannot feed itself. Its sole purpose is to consume the food brought by the workers, growing exponentially in size. It is during this crucial period of larval development that the future role of the ant is often determined. This is known as trophic switching. The specific quality and quantity of protein and fats fed to the larva by the nurses dictates whether it will mature into a minor worker, a major soldier, or, potentially, a new queen. The larvae are the destiny of the colony. Next comes the pupa, a quiet chrysalis state where the body is dramatically reorganized. Some species, like the common wood ant, spin a silk cocoon for protection. These cocoons are often mistakenly called ant eggs by the uninformed. It must be integrated into the colony's workforce, its first task being to learn the nest's unique chemical signature. But the individual ant is meaningless in isolation. It is a replaceable, disposable cog in a machine so vast, scientists have coined a special term: the superorganism. A superorganism is a social unit of independent organisms that collectively functions as a single physiological entity. Think of it like a massive body. The queen is the reproductive organ. The foragers are the digestive system, bringing in fuel. The soldiers are the immune system, constantly patrolling and defending. Ants are the original civil engineers. The nest, or formicarium, is more than just a home. It is a meticulously designed, climate-controlled, secure, and highly specialized infrastructure that can extend dozens of feet underground. The complexity of these subterranean networks can often exceed the footprint of a human city above ground. The construction begins with the excavation of the first chambers by the queen or a small group of workers. They remove individual grains of soil, packing them strategically or dumping them to form the characteristic mound above ground. This mound is not just a trash heap. It serves multiple critical functions. It's a defensive barrier, a flood defense, and most importantly, a solar collector, helping to regulate the internal temperature of the nursery chambers below. These underground cities contain specific rooms for specific functions: deep, high-humidity nursery chambers for eggs and larvae, dry chambers near the surface for pupae, and vast food storage chambers for seeds, fungi, or captured prey. The network of tunnels that connects them is often designed for maximum efficiency and airflow, ensuring adequate ventilation and humidity control. For instance, deeper tunnels often act as condensation sinks, allowing the colony to draw moisture from the air, while shallow tunnels can be sealed off during extreme heat. They are masters of thermoregulation, using the depth of the earth and the orientation of their mounds to keep the brood at the ideal, constant temperature necessary for survival. Furthermore, many species cleverly utilize the roots of large trees, weaving their tunnels around them for structural stability and protection against erosion. How does a creature less than a centimeter long, operating without a master architect, coordinate the construction of a superstructure? The answer lies not in planning, but in physics and instinct. Ants build using immediate, local environmental cues. For example, when building a tunnel, workers will deposit a grain of dirt at an angle that maximizes structural stability based on the gravity and friction of the surrounding soil. When multiple ants follow this simple rule, place the dirt in a stable spot, the result is a self-organized, near-perfect arch, a structure that is inherently strong against collapse. This is known as stigmergy, where the work itself leaves a physical cue that guides subsequent labor. Furthermore, they possess an innate understanding of load-bearing capacity and material engineering. They will often mix saliva with soil, creating a stable, cement-like material or a highly effective waterproof plaster, especially in chambers prone to collapse or flooding. They are experts at erosion control, sometimes laying down small pieces of debris to stabilize entrance points. When building in wood, they chew precise galleries, often reinforcing the surrounding wood structure itself with their secretions to prevent the tree from cracking or falling over, protecting their home from environmental stress. Collective digging is also optimized. One ant starts digging, and when another detects the disturbance, it often begins digging cooperatively, ensuring rapid, synchronized material removal. The colony's external world is connected by vast, intricate highways of pheromones. Imagine a city where every citizen has an invisible map, visible only to them, updated in real time by scent, color-coded for urgency and destination. This is the ant trail. The traffic flow is incredible. It's a dynamic system where the intensity of the chemical signal dictates the speed and number of recruits. A fresh, strong pheromone trail means high-quality food and high urgency. Critically, these pheromones are volatile and decay over time. If the food source runs out, the workers stop refreshing the trail, and the path slowly vanishes, an efficient self-cleaning system. When a trail becomes too congested, ants instinctively switch from following the primary, central trail to creating parallel lanes. They even adopt a form of lane keeping. Inbound traffic, ants carrying heavy food, often sticks to one side of the trail, while outbound traffic, empty foragers, takes the other, moving faster. This prevents head-on collisions and maximizes flow velocity. This collective movement is not chaotic. It's an optimized flow that consistently finds the shortest path to a food source, effectively executing a biological algorithm. The density of ants on a trail can exceed what we observe in our most crowded urban environments, yet jams are incredibly rare, all governed by the subtle, self-regulating rules of pheromonal intensity and local density cues. Recruitment is the heart of ant logistics. When an ant finds a large food source, say a dead beetle, a dropped seed, or a pool of nectar, it doesn't try to carry it alone. It executes a complex, nuanced recruitment strategy tailored to the situation. For low-urgency complex routes, some species use tandem running. A successful forager leads a single recruit back to the food source. The follower keeps close, constantly tapping the leader, learning the precise turns and landmarks along the way. This method transfers navigational knowledge efficiently, rather than just relying on a blind chemical trail. For high-urgency finds, the forager may lay an intense emergency pheromone trail back to the nest. This chemical signal is intense and decays rapidly, indicating extreme urgency and high reward. Inside the nest, the forager physically communicates the find through a distinct vibration or dance, and crucially, through trophallaxis, the exchange of liquid food stored in a specialized stomach called the social stomach, or crop. This exchange transfers the scent, taste, and even trace amounts of pheromones related to the food source directly to the other workers, providing immediate, high-fidelity information about the quality of the discovery. The result is an exponential effect. The first few recruits return to the nest, lay their own, stronger pheromone trails, and recruit even more workers. Within minutes, a trickle of individual ants becomes a devastating, overwhelming column capable of dissolving and relocating large food sources in a single afternoon. This self-amplifying system allows the colony to instantaneously scale its workforce and logistics to meet the need of the moment, demonstrating incredible resource efficiency.